Welcome to the Explainer. Today, we're getting under the hood of the software you use every day to talk about a really cool technology that makes everything run faster, just-in-time compilation.
So here's what we're going to cover. We'll start with a basic problem JIT was made to solve. Then we'll see how it actually works its magic. We'll also look at where you can find it in the real world. And of course, we'll get into the trade-offs that come with all that power.
All right, to really get this, we've got to start with a fundamental conflict that's kind of at the heart of all software performance.
I mean, you felt this, right? Why is one app super sluggish while another, doing basically the same thing, just flies? A huge part of the answer is how a program's code gets translated into a language the computer can actually understand.
This brings us to the two classic ways of doing things. On one side, you've got the interpreter. Think of it like a live translator at the UN. It translates speech line by line right on the spot. It's super flexible, but all that real-time work can really slow things down. Then, on the other side, you have the compiler. This is more like someone who translates a whole book. They do all the hard work up front, converting the entire program into fast, native machine code before you even run it. The result is incredibly fast, but it's a much more rigid, all-or-nothing process. And you can really see that difference here. The interpreter on the left is stuck in this constant loop. Read a line, do the thing, read the next line. But the compiler on the right, it does its job once, creating this totally separate, optimized program that the computer can just run directly. So for a long time, developers were stuck with this choice. Did they want the easy flexibility of an interpreter or the raw speed of a compiler? But what if you didn't have to choose? And this is exactly where just-in-time, or JIT, compilation comes in. It's this really clever hybrid approach that tries to give us the best of both worlds. It makes the decision to compile not before the program runs, but while it's running. And that's really the holy grail right there, isn't it? The whole point is to get the pure speed you get from compiled code, but keep the dynamic, on-the-fly nature of an interpreter. So how does this actually look in the real world? Well, in systems like the Java virtual machine, your code first gets turned into this intermediate language called bytecode. The program starts out just interpreting this bytecode, but behind the scenes, the JIT compiler is watching, just waiting to jump in and create super optimized machine code for the parts of your program that are doing the most work. Okay, but that leads to the next big question, right? If it's compiling while the program is running, how on earth does it know which parts of the code are the important ones to optimize? It follows this really simple but super powerful process. Think of it like a city planner watching traffic. First, it just interprets the code, but it's also profiling. It's watching to see which roads get used the most. When it finds a piece of code that's being used over and over and over again, what it calls a hotspot, that's like finding a super congested highway. So it rebuilds that one specific road into an expressway by compiling it into machine code. The rest of the little city streets are left alone, but the next time traffic needs that highway, it gets to use the new blazing fast version instead. But there's a catch. This whole process of watching traffic and rebuilding roads, it isn't free. It takes time and it takes processing power, which means there's this initial delay before you get to feel those speed benefits. This is what's known as warm-up time. And it's a fascinating trade-off because it means a JIT-powered program is actually slower at the very beginning than a program that's just being interpreted. It has to pay that upfront cost of profiling before it can cash in. But once those hotspots are compiled, the long-run performance can be unbelievably better. A perfect example of this is PyPy. It's a version of Python that uses a JIT compiler. For programs that run for a while, it is, on average, a whopping 4.4 times faster than the standard Python interpreter. That's a massive speed boost. But here's the price you pay. During that initial warm-up, while it's still trying to figure out what to compile, PyPy can actually be about 5 times slower than the standard version. It's a classic case of short-term pain for long-term gain. So where is this powerful tech actually being used? Well, it turns out it's pretty much everywhere. It powers a lot of the applications you're probably using every single day. So yeah, we've seen it in specialized Python environments like PyPy, but honestly, the most common and impactful place you'll find it is in the world of JavaScript. Every single modern web browser relies on a JIT compiler to make websites and web apps feel fast and snappy. And this table shows you all the heavy hitters. You've got Google's V8 engine, which powers Chrome and Node.js, and it's all about raw execution speed.
Then there's Mozilla's SpiderMonkey and Firefox, which really focuses on sticking to web standards. And in the Apple world, you have JavaScript Core, which is tuned specifically for great memory and energy efficiency on things like iPhones and Macs. They all use JIT, but they all tune it for slightly different goals. But as powerful as JIT is, that warm-up time we keep talking about means it's not the perfect tool for every single job. And this brings us to its main alternative.
You know, it really all comes down to balancing the pros and cons. JIT can give you incredible peak performance, and it can make optimizations based on how the program is actually being used. But the price you pay is that startup delay, and often using up more memory to store both the original code and the new compiled versions.
So, for those times when a startup delay is just not an option, there's another way. Ahead of time, or AOT, compilation. This is kind of like that traditional compiler we saw at the beginning. It does all the work up front, creating a native program that's ready to run instantly with zero warm-up needed.
And you see this used all the time in mobile app development. A great example is Meta's Hermes engine, which is used for React Native apps. Think about it. On a phone, when you tap an app icon, you want it to open now. You can't afford to wait for a long warm-up, so AOT is the perfect choice for that instant-on feel. This chart just nails the central trade-off perfectly. Look at startup time. AOT is almost instant, while JIT has that noticeable delay. But then look at peak performance. Because JIT can see how the code is actually running, it can often make smarter, more aggressive optimizations and achieve a higher top speed in the long run compared to the more one-size-fits-all approach of AOT.
And all of this leads to a pretty fascinating final thought. This constant tug-of-war between JIT and AOT really proves that how we run our code is just as important as the code itself. It really makes you wonder, are we headed towards a future of these hyper-specialized compilers, each one perfectly tuned for a very specific job, whether it's for a web server, a mobile app, or some tiny smart device? It's a powerful reminder that in the world of software, the quest for speed never, ever ends.